Hi everyone, this is lesson 7 of module 5, comparing linear functions and graphs. So in this lesson we're going to be looking at different representations of functions. We will see them as tables, graphs, equations, or just descriptions, and we'll be looking to compare those equations and specifically looking at the rate of change represented different ways. Okay, so we're going to look at exercises 1 through 4 first, and they give us information about functions, and you're just going to use the information given and answer the questions. Okay, so the first one says that Alan and Margot drive from city A to city B, a distance of 147 miles. They take the same route and they drive at constant speeds. So Alan begins driving at 1:40 p.m. and arrives at city B at 4:15 p.m. Margot's trip from city A to city B can be described with the equation y equals 64x, where y is the distance traveled and x is the time in minutes spent traveling. Who gets to city A from city A to city B faster? Okay, so first thing I want to do is point out a typo for you. This is not minutes, it must be hours, because otherwise she'd be traveling at a pretty fast rate of speed, right? 64 miles per minute, and also we're going to have to assume that the distance here is miles, because they don't tell us otherwise. So if her distance is miles and so is 64x, 64 miles per hour is a much more reasonable speed than 64 miles per minute. Okay, so that leads me to, for Margot, we can see from her equation y equals 64x. Remember in this format here, the coefficient of the x term is the rate. So 64 is going to be miles per hour. So Margot goes 64 miles per hour. Okay, so that was a little easier with the equation. But Alan is going the distance is 147 miles. Okay, so we need to know the amount of time to put his rate together. He goes 147 miles in a certain number of minutes. Let's figure out how many minutes it is from 1:40 p.m. to 4:15 p.m. So if you're like me, you do this in parts. So from 1:40 to 2 would be 20 minutes. I'm going to start adding it up here. 20 minutes. And then from 2 to 4 would be 2 hours, so that's 120 minutes. And then another 15. So his time is 155 minutes. All right, that's the way I do that. So 155 minutes is his speed there. So he goes 147 miles in 155 minutes. So we need some way to compare these two rates here. One of them is in miles per hour, the other one is in miles per minute. So I'm going to do something that's going to just make the math a little bit easier. So this is Alan's rate here. Let's just label it on my work here. Alan's rate is that. I'm going to rewrite Margot's rate in miles per minute. So she goes 64 miles in 60 minutes. Okay, so now I'm going to try to compare these two fractions, this one here and this one here. Now I can put them in the form of decimals and compare them that way. But if I look at them for just a minute, I can tell that all I need to know is who gets from city A to city B faster. So which one of these fractions is bigger? Which is a bigger number? Well, I can tell that this one here is less than 1. on this one here is greater than 1. 64 over 60 is greater than 1. 147 over 155 is less than 1. So I know that 147 over 155 is less than 64 over 60. So Margot is faster. Margot's rate is faster. So she is going to get to her destination sooner. Margot's rate is faster. Okay. Other ways you could do that, you could have converted them both to miles per hour. We could have put these in decimal form to compare miles per minute. But if you're like me, you like to get there the fastest way. So there's another way to do it. Okay, so we had a function represented just by a description telling us what time he started driving and what time he got there and how far it was. And then the other one was given by an equation, but we could compare them just by doing a little bit of rearranging of the facts here. Okay, let's look at the next one, exercise 2. Exercise 2 looks a lot like the extra problem I gave you on the end of Module 4 assessment. So if you did that problem, you're going to really like this problem because it's a little bit easier. So let's look at it. You have recently begun researching phone billing plans. Phone company A charges a flat rate of $75. A flat rate means that your bill will be $75 each month with no additional costs. The billing plan for phone company B is a linear function of the number of texts that you send that month. That is, the total cost of the bill changes each month depending on how many texts you send. The table below represents the inputs and corresponding outputs that the function assigns. At what number of texts would the bill from each phone plan be the same? At what number of texts is phone company A the better choice? And at what number of texts is phone company B the better choice? So go ahead and pause the video and work on that for a little bit. See if you can figure out what number of texts is going to be kind of the dividing line for this. Okay, so we could start by writing the equation for phone company A. So phone company A, if Y is the total cost, we could do that. We could let Y be the total cost. And I'll write that here. Let Y. If Y is the total cost, then the equation is just Y equals 75 for phone company A. Y equals $75. Okay, so for phone company B, we're not told how much is charged for each text. We don't know the rate of change, in other words, of the cost of the bill. So we need to find that from the table. So one thing I can notice is when I go from 50 texts up to 150, that's a change of 100 texts. My bill goes up $10. So I can use that to figure out the cost per text, right? So I'm going to pay $10 for every 100 texts. Another way of looking at that is just the rate of change, right? So it's 60 minus 50, the change in the output, the change in the Y value. This is Y. We'll let this be X. Over the change in the input, the number of texts. So this would be 150 minus 50. Okay? So that's what we have there. $10 for 100 texts. And we could just to make sure that it's consistent, we could compare another set of points. So we would have 500, I'm going to turn this one around, or no, So the output goes on top. 95 minus 65 over 500 minus 200. Okay, so this would be $30 for 300 texts. So we can see this is constant, right? Texts. It's pretty easy to see those. That is the same rate right there. So what is that rate? 10 hundredths. 10 divided by 100. So this is equal to 10 cents per text. $10 for 100. This is 10 divided by 100 is 1/10. So that is our rate of change there. 10 cents. So 10 cents for every text. So what is the equation? What is this equation then? Okay, remember that I know that I can write every linear equation. I'm going to give myself some room here. Okay, so that's what we came up with for that. So I know that I can always write a linear equation in y equals mx plus b, where m is the rate of change and b is the y-intercept, or we can think of it kind of as the starting point. So for this equation, I'm going to say the total cost, y, is equal to 10 cents, or $0.1, times the number of texts. So this is 0.01, 1/10 times x, plus some starting point. Okay, so there might be an initial cost for this phone company. Okay, so that's my basic equation. So I need to find out what this is. So to find out what that is, I can plug in one of the sets. So I know that I pay for 50 texts, I pay $50. So $50 total cost is equal to 0.1 times the number of texts, which is 50. Again, I pay $50 for 50 texts plus some starting point. So 10 cents times 50 is going to be $5. So I've got here 50 is equal to 5.00, $5 plus b. Okay, so that represents, the $5 here represents the cost for the 50 texts, right? And then b is kind of the flat rate cost, the starting point for this. If I had 0, if I didn't text anybody, I would still pay this much. Okay, so y would equal b when x is 0. All right, so what is b then? So b, right here, subtracting 5 from both sides, b would have to be $45 here. So my equation for phone company, so this is A. So my equation for phone company B is total cost y is equal to 0.1 or 1/10 times x plus 45. Okay, so hopefully some of you are thinking system of equations, because what's our question here? Our question here is right in here. At what number of texts would the bill from each phone plan be the same? And then when is company A the better choice and when is company B the better choice? All right, so I'm going to get a new page here so we can work this out. And you might want to pause and work it out yourself now. Okay, so here are our two equations. So if I want to know when the cost will be the same, then I can solve this system and find an XY pair where they're the same. So this is nice when both equations are written in slope-intercept form. I have y is equal to something, y is equal to something. I know that where these have the same value, that the y values are the same, so I can just say that 75 is equal to 0.1x plus 45. So in other words, when these two expressions for total cost are equal, that's when the cost for both companies is the same. So now I just have one variable here to solve for, and it's the variable for number of texts, right? X tells me how many texts. So I'm going to subtract 45, and I'll get that 30. Draw a line here. On the left-hand side, got 30, and on the right-hand side, 0.1 times x. So this is, I'm going to actually do this because I like not having to use a calculator if I can get away with it. So I'm going to think instead of 0.1, that is 1/10, the fraction 1/10. So what I'm going to do here is multiply both sides here by 10 now to get rid of the 1/10, so I can solve for x. And I will get an equivalent equation here. 10 times 30 is 300, and that is equal to x. Okay, so what my math here is telling me is that at 300 texts, the cost will be the same for both companies. So let's go back. We haven't really focused on the table too much. Whoops. We use the table to find the rate of change, but what do we notice from the table is that I go with 50 texts, company B is $50, which is cheaper than 75. Okay, so cheaper for 150 texts, still cheaper for 200 texts, still cheaper, $65. For 500 texts, now it's $95, so it's more expensive. So I know at least if I'm going to get 500, I'm definitely going with company A, $75 a month. So it's somewhere between 200 and 500. And so our algebra, solving that equation, gave us that same result right there. 300 is equal to x. So the answer then would be so if I had more room, I'd use more words. But basically, it's go with company B for 0 to 300 texts, and go with company A for 300 or more texts. So remember, whoops, this was company, I keep trying to write up there. Company A is right there. Company B is this one. So fewer texts, then do the one that has the per text charge. And lots of text, go with the other one. Okay, so that was similar to the problem you had at the end of Module 4 with a little bit of a twist. Okay, so let's look at another one now. Okay, exercise 3 says, a function describes the volume of water, y, that flows from faucet A in gallons for x minutes. Okay, so the graph below is the graph of this linear function. So the x-axis is time in minutes, and the y-axis is volume of water in gallons that flows. Okay, so faucet B's water flow can be described by the equation y equals 5/6 x, where y is the volume of water in gallons that flows from the faucet in x minutes. Assume that the flow of water from each faucet is constant. Which faucet has a faster rate of flow of water? Each faucet is being used to fill tubs with a volume of 50 gallons. How long will it take each faucet to fill the tub? How do you know? And the tub that is filled by faucet A already has 15 gallons in it. If both faucets are turned on at the same time, which faucet will fill its tub faster? Okay, so there are a couple questions to address. First of all, how long will it take each faucet to fill the tub? And then we'll be explaining how we know that. And then also, we'll look at the situation where there's already 15 gallons in one of the tubs, the tub filled by faucet A, and then looking at which tub would fill fastest in that situation. Okay, so we've got an equation and a graph. So the graph is for, let's look at it again. The graph is for faucet A. So I'm going to just put that, well, I'll put it up here at the top. The graph is for faucet A. And then faucet B is the equation y is equal to 5/6 x. Okay, so what does this mean? Well, y is gallons, x is minutes. So every minute, 5/6 of a gallon of water goes in the tub. Okay, so almost a full gallon per minute. Not quite. So what we need to know is faucet A's rate, and it's a constant rate, I can tell by the graph. So I need to find the rate from this graph. And so I see a point right here that crosses grid lines. So it's a nice point to use for the slope. So it's right there. And I'm going to draw a slope triangle here. So I know some of you are still like, shaky on this, but getting it, but it just takes more practice. So it's nice because this lesson is giving us practice. So this distance here is 4. It's not just 4, it's 4 gallons, right? Because it's the distance on the y-axis, which is gallons there. So this leg of the triangle represents 4 gallons. So this leg of the triangle, we go from 0 to 7 minutes. So it is 7 minutes. Okay. So what is our rate for faucet A? It's 4 gallons in 7 minutes. So we can think of it as 4/7 gallons per minute. Okay. So we need to compare, well, let's write the equation first. So if it's 4/7 gallons per minute, we know that the equation for faucet A then is going to be y is equal to 4/7 x. Okay, so for every minute, 4/7 of a gallon is going to go into the tub. Okay. All right. So I want to compare these rates, and I'm just encouraging you with these whenever you can, just to leave things as fractions. We don't want to be rounding things off, and we can often do simple comparisons. So which one's faster, 4/7 or 5/6? So I want to compare these fractions, 4/7, which is just a little over a half, and 5/6, which is pretty close to 1. So I can argue that 4/7 is less than 5/6. There's quite a few ways that I could argue that. But I don't have to get a common denominator. I don't have to change them into decimals. I can just reason that 4/7 is quite a bit smaller than 5/6. So faucet A is slower. So but we're asked more than that. We're asked how long it will take to fill the tubs. So I'm going to get a new page here so we can have more room. Okay, so now I'm going to use the equations to figure this out. And remember, hopefully you have all the skills you need to be able to do these problems. So it's fine if you want to follow along for examples, but you're going to learn a little bit more if you tackle them yourself first. Okay, so if the total output, the gallons that flow is y, is equal to 4/7 times the minutes. So the gallons flowing is a function of the time that the faucet is on. I can solve this equation for minutes. So I know that the tub is 50 gallons. So I want to know how long does it take for 50 gallons of water to flow out of this tub. And then I also want to know for faucet B the same question. 50 is equal to 5/6 times x. So I just substituted 50 gallons for the output of this function, and I'm going to solve for the input. So in order to solve these, I want to multiply by the reciprocal. Whoops, that's not the reciprocal. I want to multiply both sides of the equation by the reciprocal to solve for x. So this becomes 350, 7 times 50 over 4 is equal to, and the 4/7 times 7/4 is 1, so this is equal to x. And now I can do the division and put that into gallons, and it becomes 87, not gallons, minutes. 87.5 minutes. This equals x. So this is 87.5 minutes. Not 0.4, 0.5. Sorry. All right, so we know faucet B is going to be quicker, right? Let's do the math and see if we can prove that. Okay, so for this one, we're going to multiply by the reciprocal to make the coefficient of x 1. Once again, so that'll be 6/5. And so on the right-hand side, I've just got x. 5/6 times 6/5 is 1. And then 6/5 times 50, I can get a common factor out here. 5 and 10, or 5 and 5 goes into both of those. So this is going to be 60. So this is 60 minutes for faucet B. So that checks out with looking at the rates. All right, so we've got one more calculation to make here. And that's how fast can the faucet fill the tub if it already has some water in it. So let's go back and look at that. The tub that is filled by faucet A already has 15 gallons in it. So if both faucets are turned on at the same time, which faucet will fill its tub faster? Okay, so we already know that faucet B can do the full 50 gallons in 60 minutes. So what we want to know is for faucet A, faucet A with 15 gallons. So what would that equation look like? So the total volume in the tub is going to be 4/7 of a gallon every minute times the number of minutes. And then I already have 15 gallons, so that's plus 15. So now I want to solve for the 50-gallon tub. So 50 gallons is equal to 4/7 x plus 15. Now, whoops, I'm getting off the page here. Okay, so I want to solve this equation. So I'm going to subtract 15 from both sides. So 50 minus 15 is 35, is equal to 4/7 x. So really what we have here is we want to know how long does it take for faucet A to do an additional 35 gallons. Okay, that's another way to think about it. Okay, so we want to take and multiply by 7/4 on each side again. So we've got 35 times 7/4 is equal to x. Okay, and so this simplifies to, let me see, 61.25, 61.25 minutes. So 61.25 equals x. So that's 61.25 minutes. So we can see here, and we could write out our answer, but even with 15 gallons already in the tub, it's still going to take over an hour, a little bit longer to fill the tub with faucet A than with faucet B. because it's just that much slower. Okay, so what did we do with this problem? We had a description of a function along with its graph that we could get the rate off of, and we had an equation that we could find the rate directly, and then we did some comparisons with that. Okay, so two people, Adam and Bianca, are competing to see who can save the most money in 1 month. Use the table and the graph below to determine who will save more money at the end of the month. State how much money each person had at the start of the competition. Okay, so we're counting the savings that they already have. So this is Adam's total savings in the graph and Bianca's in the table. If you're feeling confident about this, why don't you go ahead and just work on it and then come back and check your work here. Okay, so let's first look at the graph and see what Adam is saving. So the graph is only showing us up to about 2 or 3 days. Let me do this. So we've got number of days down here, number of days down at the bottom, and total amount of money for Adam over here. So it looks like on 0 days, so right at the start, Adam already has $3. His total amount of money is already 3. And then we can tell by the slope of the graph, it looks like every day his amount goes up by, these are each standing for 1, so by $3. So he's saving $3 every day. Okay, it's a straight line, so we can assume it's constant. So we could write an equation for Adam's savings. His rate of change is $3 per day. And he started with $3, right? So his total savings is Y. Here's Y and X, right? So his total savings Y is going to be equal to his savings per day. So it's 3 times the number of days, X, plus the $3 that he started with, which is our y-intercept here. Okay, so once again, all these functions can be written in slope-intercept form. Y equals mx plus b. Okay, so he's saving $3 every day. So let's see if it works. So for 2, 3 times 2 is 6, plus 3 is 9. So for 2 days, I can come over here and read 9 is the amount saved. Okay, so double check that equation. So Bianca's, we have a table for Bianca. So we're going to have to look at some of the points on this table, some input-output pairs, and see how much Bianca is saving every day. So we're given for 5, 8, 12, and 20 days her total amount of money that she has saved. So we're going to have to figure out where she started, how much she had to start with, and then how much she is saving every day. Okay, so let's look at that. So between day 5 and day 8, she went from 17 to 26. So we can find this rate of change here. So 26 minus 17 is the change in the output, or the change in Y. And then that was over 8 minus 5, or 3 days. So 26 minus 17 would be 9. 8 minus 5 is 3. So it looks like she is also saving, so this is dollars, and this is days. She's also saving $3 per day. So it's going to come down to who started with the most money. Okay, but before we move on, let's check a couple other. We want to make sure this is a constant rate that Bianca is saving at. So let's check 2 more pairs of points. So I'm going to check the next two. So 38 minus 26. And she did that. She went from $26 to $38 in 4 days, from 8 to 12. So this is over 12 minus 8. 28 minus 36 is 12. And 12 minus 8 is 4. So $12 in 4 days is also $3 per day. We'll check the last pair and then we'll assume this is linear. So 62 minus 38 over 20 minus 12. 62 minus 38 is 62 minus 40 would be 22, add 2 more, so it would be 24 over 20 minus 12 is 8. 24 divided by 8 again gives us that $3 per day of savings. So her table, by checking the slope between all of these points, or checking the rate of change, I find that she's saving the same at the same rate as Adam, $3 per day. Okay, so all that's left to find out is what she started with and how much they'll have at the end of the month. Okay, so let's get a new page here. Okay, so we still need to find out how much Bianca started with, and that's going to be kind of this y-intercept right here. So we know that at day 5, she had $17. So we know that 17 is equal to 3 times 5 plus b. So 17 is 15 plus b. So we know that b equals 2. Okay, so her equation is y is equal to 3x plus 2. So she started with $2. And so we can conclude that she's going to have more money at the end of the month than Adam does. Okay, so since they're saving at the same rate, they will save the same amount of money in 30 days or 31, whatever their month is. But Adam will still have more because he started with 3. So depending on how you interpret that question, you would answer it differently. So, okay, so there's Adam and Bianca. So we went from a graph to a function written as an equation, and we went from a table to an equation for Bianca, and we could get lots of information there. Okay, so that is lesson 7. Really not any new information here. We just worked with lots of different representations of functions, and we pulled different pieces of information out of them. So good luck with the problem set on this one, and we'll see you back here for lesson 8.